chapter will be focusing on chemical thermodynamics. Now, chemical thermodynamics is about the study of energy of chemical reactions. Now, this becomes a pretty key question because if we think back to the chapter on reaction rates, which talks about how fast reactions happen, one of the key determining factors there was the activation energy of the reaction, that reaction hump that we had to get over. So energy plays a pretty important role in how fast reactions happen. And if we recall back to the chapter on equilibrium, the equilibrium depended on the relative rates in the forward direction as well as the reverse direction, which again depends on that energy part to it. So energy is going to play a pretty critical role in both kinetics and equilibrium. So this chapter we're going to try to go into that energy part in more depth. Part of the chemical thermodynamics we've gone over before, the enthalpy. And remember, the enthalpy is the change in heat, or the heat that's transferred between the system and the surroundings during a constant pressure process. The other thing that we've talked a little bit about, but we haven't got into in full detail, is the entropy, which has to do with the randomness of the substances in a chemical reaction or process. When we think about both enthalpy and entropy, it's natural for us to think about what tends to happen in nature, what drives natural processes, and so it's going to lead us to a discussion of spontaneity and looking at the chemical reactions or physical processes from the standpoint of whether these things will happen spontaneously under a given set of under a given set of pressures and temperatures or conditions, or whether they'll be spontaneous in the reverse direction, or whether they're at equilibrium. So we'll answer kind of those questions. The sections in this chapter will start out again addressing that idea of whether processes are spontaneous or not, and then we'll go into entropy in more depth and how we determine entropy and quantify it. And then we'll get into Gibbs free energy, which will bring together both entropy and enthalpy in a quantitative sense. And then we'll take a look at that from the temperature perspective and relate that back to both kinetics and equilibrium. When we look at whether a reaction is spontaneous or not, recall back from our study of thermochemistry that we definitely associated a loss of energy as a spontaneous process. And we noted that the change in energy was equal to Q plus W. So the heat exchange with the environment plus the work done by the system. We also noted that due to the first law of thermodynamics that there had to be a conservation of energy. The energy lost had to be gained by something else, and so we had to account for all of the energy in the system and the surroundings. Now, what this didn't take into account was the degree to which reactions happen. And so that's what we want to get to now, is whether or not there's you have to add energy or remove energy. Is the process going to be spontaneous? And it's not always about the energy, is what we'll find out. When we look at certain processes, so in the flask here we have the expansion of a gas. So in flask B, we have all the gas, and then flask A is empty. If we open up the valve in between them, the gas will spontaneously spread out, so it's in the direction going downward here, to where it's spread out into both A and B. And the odds or the chances that the gas will then spontaneously all go back over to B is not going to happen. So you have a spontaneous diffusion of the gases and spreading out, but the chances of them going back to all being in one flask is not going to happen. So it would be non-spontaneous. Another example of spontaneous and non-spontaneous would be the rusting of a nail. We know that if you leave a nail out, it will spontaneously rust. Now you may have to add some other factors into it, but that nail is going to spontaneously rust. It will not go from a rusted state back to the clean state, so it will not go back. Will not go backwards. So that would be non-spontaneous. So all reactions are going to be spontaneous in one direction and non-spontaneous in the other direction. The other thing we find that this spontaneity is influenced to a great extent by temperature for many different processes. So for instance, the melting of ice. If we're at a temperature above 0 degrees Celsius, we know that ice will spontaneously melt. I'll go in this direction here. If we happen to be below 0 degrees Celsius, then the spontaneous process is in the reverse direction. So we can see that temperature is going to play a role in whether or not many chemical and physical processes are spontaneous or not. The freezing of water also demonstrates another very important part about spontaneity, and that is that it's not just energy dependent. I mean, obviously the exothermic process here is going from the liquid to the solid. Right? That's the process that is minimizing energy, and of course that's not always spontaneous. It'll spontaneously go, if you're at a temperature above 0 degrees Celsius, it's going to go spontaneously to the higher energy state. And this happens in a lot of other things. We've seen dissolving, where even though it requires energy to dissolve many solids into water, that process still happens. And as we've talked about before, that's going to bring us into the idea of entropy. And looking at the randomness that occurs. Recall that when we talked about thermochemistry, one of the things that we brought up were state functions and non-state functions. And we knew that temperature, internal energy, enthalpy were all state functions, and which meant that they didn't depend on the path that we took to get there. It only depends on the initial and the final state. Well, one of the things that this is going to bring into play is whether or not processes are reversible or not. And recall that the other, in terms of the energy, remember we had Q plus W, the heat exchange plus the work, those are not state functions, so they depend on the path that you take to get there. So this idea of reversible processes is going to be an important one for us to spend a little bit of time trying to understand. Early development in this study of reversible processes happened in the 1800s, where they were looking at steam engines, and they realized that steam engines, there's no way to convert all of the energy, all the chemical energy in the fuel to the propulsion of the steam engine. That some of it was always lost due to heat, but they were able to figure out that there was some relationship between that heat and the temperature. And so they came up with, and this was a person by the name of Rudolf Clausius. He's a German physicist, and he came up with the ratio of the heat exchange over the temperature as being having a significant influence on this process of the steam engine. And he called this ratio of the heat exchange to temperature the entropy. Right, so this is the beginning of entropy. I guess suppose he intentionally actually named it close to enthalpy because he knew it had something to do with the energy that was being gained or lost in the process. A reversible process, then, was one in which the changes could be completely reversed simply by reversing the changes that had happened, exactly the way that they had happened. So you could completely restore the system to its original conditions with no change in either the systems or its surroundings. And for an engine to have its maximum efficiency, all the processes that would happen were believed to be reversible, or if you had all reversible processes, you would have the maximum efficiency of the engine. So what we find out then is that the work done by the maximum work done by the engine would be equal to the amount of work that was reversible. In other words, that you could do in a reversible sense. On the flip side of this, an irreversible process is a change that cannot be restored, or that you can't simply reverse the process to restore the system and the surroundings to their original conditions. So these ideas of the maximizing your work output become much more significant from a physics standpoint. So we'll leave that discussion to your later studies in physics. If we look at reversible processes, a couple of examples here. In the pictures to the left, you have a system where there's a higher temperature in the system, and so you spontaneously get heat being transferred out of the system into the surroundings. And so heat would not spontaneously go back in as long as the temperature of the system were higher. So that would be a non-spontaneous situation. However, if the two temperatures were the same, right, you can imagine a very, very small change in temperature on one side or the other directing heat toward the one that's at lower temperature. And if you change that, again, that same that same small amount, you raise the other one the other way, then the heat would flow back in the other direction. So heat flow actually is a reversible process if you consider a very, very small change in the system, the surroundings. So from that standpoint, we can conclude that reversible processes are those that reverse the direction whenever there's an infinitesimal change made in some property of the system. So a very small change. So if you can get a process to reverse directions just by making a small change, then we can refer to that as a reversible process. An irreversible process, that cannot happen. So for instance here, over on the left we have a piston with a gas enclosed in it, and a vacuum on the other side where the piston is in a movable partition. So if we pull that partition out and we look at the middle, the gas is obviously expanded through the vacuum area. And so that expansion of the gas into that vacuum would be an irreversible process because there's no small change that we can do to make it go back the way it was at the beginning. In order to go back to where it was at the beginning, we would have to add work. And so by adding work, we have changed both the system, the gas that's inside the piston, and we have changed the surroundings because the surroundings had to do work on that system. So the expansion of a gas would definitely be an example of an irreversible process. Right, so as we look at this then, an irreversible process, they cannot be undone by exactly reversing the change to the system. And spontaneous processes, this is an important part to remember, a spontaneous process is always irreversible. Right? So spontaneous processes are always irreversible. Now, that's not to say that, so any spontaneous process is irreversible. That's not to say that the reverse procedure can occur. For instance, we can, if we look at, say for instance, the formation of water from hydrogen and oxygen. That process is spontaneous in the positive direction. You need a little bit of energy to get started, but hydrogen and oxygen will spontaneously produce water. We can make that go in the opposite direction, but we have to add energy to it. And the fact that we have to add energy to it means that it's, continuously, means that it's not spontaneous. Again, as opposed to taking hydrogen and oxygen, combining those with a little bit of spark, we can get them to spontaneously form water. But again, we can't make them go back the other way without adding energy. So even though processes are spontaneous in one direction and irreversible, it doesn't mean that we can't use external sources to make them go the other way. It's just that in doing that, we'll change both the system and the surroundings. All right, so next we'll move on to talking a little bit more about entropy and the second law of thermodynamics.